So this is going to be a very short lecture on optional stopping. So there will be another lecture on optional stopping later, which is going to be much more involved, and it will present the optional stopping theorem, which is very nice. But for now, we're going to talk about a simple theorem that is related to stopping times, and it's very useful. We already hinted on this theorem before. So suppose that we have xn, a submartingale. So before I state the theorem, let me just say that this means, in particular, that the expectation of xn is larger or equal than the expectation of xm if n is larger or equal than m. So for submartingales, the expectation is growing. So what we are going to do is something similar, but not for fixed times like here, but rather for stopping times. So we also fix t is stopping time. And here, very importantly, we will assume that t is bounded by n. So there exists some n such that t is uniformly bounded as a random variable by this n. Um, and then we will prove that the expectation of x0 is smaller or equal than the expectation of xt, which is smaller or equal than the expectation of xn. Okay, so this, if you look, has a very similar taste to the green inequality here concerning the expectation of deterministic times n and m, but it's generalized to random times x0, x and xt and xn. Now, I'm gonna give the full proof of this theorem now, but I would like to just say a word about what this random variable actually means. We know that x is a random variable. Sorry, xn is a random variable for every n, or rather xi. So this is what we mean by being a random variable, right? That we can take this function and evaluate at some point in our sample space. And what xt means is that first we're going to use this random variable t to select an integer. Now we are talking about this random variable, and we're going to evaluate this random variable at omega. And what I'll leave for you as an exercise is to prove that xt is measurable. If we're talking about its expectation, we definitely need it to be measurable, but it's not a hard exercise. Actually, by just looking at the proof of this theorem, you can have already some hints on how to do it. Let's go to the proof of our main theorem. So first let's let us recall that we defined this predictable process hm, which takes an integer and just asks if our stopping time is strictly smaller than this integer. So if this is our stopping time, h is going to be 1 here until t minus 1. So this is predictable. So it's the indicator function. This is predictable. So that means that the stochastic integral of x against h is also a submartingale. Another way to write this process is as x t minimum m minus x0. So what do I mean here? So this process is gonna follow xi minus x0 until t minus 1. So that's why until t minus 1 it's equal to this process here. Because until t minus 1 this is just m. After, this process will stop evolving. So it will follow x until time t, and then it will stop evolving. And this is also happening with this process here because we are taking the minimum with t. So when m becomes larger than t, it stops moving. Okay, so why is it interesting to state this? Because now we see that this is also a submartingale. Because it could be written as an integral of another submartingale. Good, so we know by the same as we wrote in green above that the expectation of this process here, x t minus t infimum m, is growing. So this is bigger or equal, for example, than the expectation of x t minimum 0 and is smaller or equal than the expectation of xt minimum n. But now let's recall that t is smaller or equal to n, so almost surely. So this is n actually. And on the other hand, this t is bigger or equal to 0, so this is 0. So this is almost all what we want. We got that the expectation of xt minimum m is between the expectation of x0 and the expectation of xn. Good. But this is not exactly what we want. What we want is to have the expectation of xt inside. Okay, so let us define again another predictable process, which is going to be the opposite of h. So k is going to be 1 minus h. So this is also predictable. Right? If hm belongs to fn m minus 1, then k being this algebraic formula is also in fm minus 1. So this process is also predictable, and we also know that kx is a submartingale. Let us look at then the expectation of xm minus the expectation of xt. This we would like to show, made a mistake here. Here I want n, so the last time. So we wanted to show that this is bigger or equal to 0, right? We want to show this side of the inequality here, that xn minus xt is bigger or equal to 0. So let's go back here. Xn minus xt n is the last time and t is almost surely smaller or equal, and we're looking at the difference of x between this time and this time. And by the same reasoning as we did with h, this is going to be shifted for the process k, but this difference is going to be the same for the process kx. So the process kx stays at 0 until time t, and then it follows the increments of x. So this is exactly kx at time n. You see that the jump from t to n is the same in the process x or in the process kx. So we know that k is a submartingale, so its expectation at time n is bigger or equal than its expectation at time 0. And any stochastic integral at time 0 is exactly 0. So we just proved that xn is bigger or equal than xt in expectation. So here we proved this side of the inequality. And now here we have that we want to show that xt is expectation of xt is larger or equal than 0, but this is, oh, sorry, I made a mistake here. This is t. The minimum between t and n is t. So here we also proved the other side of the inequality, that expectation of xt is also bigger or equal than the expectation of x0. So combining the fact that hx is a submartingale and the fact that kx is a submartingale, we obtain the two inequalities that we wanted. Okay, one is between 0 and t, and the other is between t and n. So this process, we more or less talked about it before when we were proving the convergence of martingales. But it's also interesting to see that this inequality holds for random times, but they have to be stopping times. So this will appear over and over during the next and the one after the next lecture. But you have to see we are requiring t to be a stopping time and we are requiring t to be bounded. We are gonna relax a bit the second condition later, but for now we are requiring a bounded stopping time. So that's it. See you in next class, where you start to bound moments of martingales.